right, so starting on Unit 10, and in Unit 10 we're going to start off with solving systems of equations, and this is something that we did back in Algebra 1, Algebra 2, you probably did it in college algebra as well, but we're going to solve systems of equation by using substitution and elimination, and we're going to do that with two variables and three variables. Okay, and that actually should be a review. And then we're going to introduce another method of solving those equations by using matrices. And we're going to do a lot of operations with matrices and learning how to use them to solve systems of equations. When we get down to matrix algebra, we're going to add, subtract, multiply, look for inverse, do determinants, and we can do this best by using a calculator. And I'll probably show you how to do these algebraically, but for speed and accuracy, we will use a graphing calculator for that. If you don't have a graphing calculator, kind of like maybe the TI-84 or the TI-Nspire, some of you may have, you can also download a matrix calculator app. So we're not there yet, but start looking for it or trying to find that calculator that you might have hidden somewhere, because it will come in very handy. So the first part of this lesson, we're going to solve systems of equations with just two variables. And we've learned three ways actually on how to do this. One way is to do this by graphing. And we're going to graph two lines and look for the point that they intersect. Then we're going to use the substitution method. And there was a typo here on both of these. That should be a plus in between them. And then lastly, we're going to look at the elimination method. So with graphing, we are going to graph now. I can do this several ways. I can use slope-intercept. I can use x and y intercepts, which is what I'm going to choose. So in this first equation, if I want to find the x-intercept, I'm going to cover up y. And I have the equation 2x equals 5. So x is going to be 2.5. So the x-coordinate is 2.5 and the y-coordinate is 0. That's why I can cover it up, because there's nothing there. Now, if I want to find the y-intercept, I'm going to cover up the x part of the equation. The x part of the equation is 0 and the y value is 5. So if I plot these points, 2.5, 0, and 1, 2, 3, 4, 5 is up here. And if I connect those, there is that line. The second equation, again, I'm going to find the intercepts. So if I want to find the x-intercepts, I'll cover up y. So I have -4 times x equals 12. So x would be -3. So the x-coordinate is -3, the y-coordinate is 0. And to find the y-intercept, the x-coordinate will be 0, and the y-coordinate here would be 2. So x is -3, 1, 2, 3, and y is 2. And I'm going to connect those points. And then what I'm looking for is where those two lines intersect. So this looks like it intersects at 1 and possibly 3. So that would be my solution, 1, 3. x is 1, y is 3. All right, so in example 2, we've got the same set of equations. We're going to solve this now using the substitution method. And with the substitution method, we want to solve one of the equations for one of the variables. So if I look at this first equation, I'm going to solve for y. And I'm just going to subtract 2x to the other side, and y would be negative 2x plus 5. Now I'm going to take this value, and where I see a y in the other equation, I'm going to plug in what y equals. So if I rewrite this sentence, I have negative 4x plus 6 times what y equals, which is negative 2x plus 5, and that equals 12. And now I'm just doing algebra to solve for x. So negative 4x minus 6 times 2 is 12x. And then 6 times 5, that's plus 30. And that equals 12. Combine like terms, this is negative 16x. Subtract 30, so negative 16x equals, 12 minus 30 is negative 18. And here we're going to see that x is negative 18 over negative 16, which is 9 over 8. Now this is close to 1, which up in this, when we were graphing, we see that close to 1, but it's not exact. When we're graphing, we're going to get estimated values, but when we're doing this algebraically, we're going to get an exact value. So in this case, x is 9/8, that's x. Now I need to plug it back into an equation to find out what y equals. So I'm going to send it back to this equation, and I will find that y equals negative 2 times what x equals, which is 9 over 8, and then plus 5. So this would be, if I cancel here, this would be negative 9 over 4 plus 5. So instead of 5, let's write that as 20 over 4. Instead of 5, 20 over 4, negative 9 plus 20 is negative 11 over 4. Whoops, that's positive 11, sorry, over 4, which is close to what we had up here. It's close to 3. Okay, but these are the exact values, and I can still write them as an ordered pair, where the x value is 9/8 and the y value is 11 over 4. Okay, x and y. All right. So technically up here, if I were to check these values, they would not make a true sentence. So 2 times 1 is 2, plus 3 is 5, that works, but 4 times negative 4 times 1 is negative 4, plus 6 times 3 is 18. And if I add these together, I don't get 12. Okay, so if I were to check my answer, that would have showed me that, this is not working in both of the sentences. So this is a good estimate, but this is the exact answer. In example 3, we want to solve the system by using elimination. And in that case, what we want are coefficients of either x or y to be opposites. Now in this equation, they're not opposites, but if I were to look at the second equation, and if I were to multiply that by 2, my x values would be opposites. I would have a 2x and a negative 2x. So I'm going to do that. I'm going to multiply the whole entire second equation by 2. So every part is multiplied by 2. And that would give me, I'm going to write the top equation first. 2x plus 3y equals 1. Now every part of the second equation, I would have negative 2x plus 2y is, and don't forget on the other side of the equal sign, that would be negative 6. All right, so now when I add these together, the 2x's are going to cancel out, or I'm going to add them up and get 0. And then I'm going to add the y's together. That would give me 5y. And 1 plus negative 6 is negative 5. So that gives me y is negative 1. Then I'm going to take my negative 1 and plug it into one of these sentences up at the top. And it doesn't matter which one you choose. So I'm going to choose the top. So I have 2 times x plus 3 times what y equals, which is negative 1, equals 1. So this is 2x minus 3 is 1. I'm going to add 3, so 2x is 4, and x is 2. So my solution, and again, I can write this as an ordered pair, xy. My solution is going to be 2, negative 1. And I would prefer that you write your solutions as ordered pairs. On the next page, we've got a word problem. Okay, this is a great example of how we can use systems of equations. But it describes a movie theater that sells tickets for $8 each, with seniors receiving a discount of $2. One evening, the theater sold 525 tickets and took in $3,580 in revenue. How many of each type of ticket were sold? All right, so we've got 2 types of tickets. We've got the regular tickets that were $8 each. So I'm going to say that this is general. So generally, the tickets are $8. And then seniors receiving a discount of $2. All right, so if I have a discount of $2, that means I'm going to take $2. My discount, or my D value, is not $2, it's $2 less than this. So the discounted tickets are $6. All right, so we have 2 variables here, and what we need to do is find out how many of each one were sold to give us a total of $3,580. So we're going to write 2 statements. First thing we're going to do is write a number statement. And that talks about how many tickets of each type were sold. So I have the number of general tickets plus the number of discounted tickets gives me a total number of tickets, which is 525. Then I need what I call is my value statement. And this has to do with the cost of the tickets. So every general ticket is $8, and every discounted ticket is $6, and all of them added up together is $3,580. All right, so now I have a system of equations. I can solve this by graphing, I can solve it by substitution or elimination, and it's up to you to pick. I know graphing is pretty much out, but I like to solve this one by substitution. So I'm going to solve for G, and I'm going to say that G equals I'm going to subtract d over here, so 525 minus d. And if I plug this in, what g equals, into the other equation, I'm going to rewrite the sentence. I have 8 times what g equals plus 6d equals 3580. So 8 times 525 is 4200. 8 times minus d plus 6d All right, so now I'm going to do two things in one step. I'm going to combine my like terms, so I get negative 2d equals, and now I'm going to subtract 4,200. And 3580 minus 4,200 is 620 negative. All right, now sometimes we worry about having a negative number down here, but notice that both of these numbers are negative, so my answer, the number of discounted tickets, will be a positive value. So my D here is going to be 620 divided by 2, which is 310, and those are both positive values. All right, so I found how many discounted tickets now I need to find out how many general tickets we have. So I'm going to take my 310 and plug it in here for D. So G, the general ticket, is 525 minus 310, which is 215. So this is the number of the general tickets. All right, so did I answer the question? How many of each type of tickets were sold? Yes, I did. I have two different types of tickets, and that's how many were sold. In example 5, here we have another system, and it just says solve. It doesn't say how to solve, so I can do this by either subtracting 2x and making this a substitution problem, or I could multiply and get one of the variables to cancel out. So I'm going to just substitute here. So I'm going to subtract 2x. So I have y is negative 2x plus 5. And I'm going to plug that in for y in the other sentence. So that gives me 4x plus 2 times what y equals is 8. So I have 4x minus 4x plus 10 equals 8. And then if I combine like terms, this comes out to be 0. So what I'm left with is 10 equals 8. And we've seen this before. This is not a true statement. So I'm going to just say this is false. And because this is false, there is no solution. All right, so if you get a problem where your variables cancel out and you don't have any variables left, check this sentence down here. If it's false, there's no solution. Now in the next one, I think we might end up with a true sentence, but let's look. All right, so here I'm gonna do substitution again. So I have y equals negative 2x plus 4, and I'm gonna substitute that here, and that gives me negative 6x minus 3 times what y equals. So this is negative 6x This is plus 6x. This is minus 12 equals negative 12. Now these are going to cancel, and I'm left with negative 12 equals negative 12. And yep, that is a true statement. And what that means here, if I were to graph this, this would be the same line. So any point on that line would be a solution to the systems. So this has infinitely many solutions. Okay, so it has lots of solutions. In example 5, if I were to graph these two lines, they would be parallel, they don't intersect, and they don't have a solution. All right, so we're going to stop there for right now, and we'll pick it up next time with looking at systems of equations with 3 variables.